Welcome to a video on MOSFET amplifier analysis. So in this video we will have a look at the steps you take to analyze amplifier. We will do some amplifier identification and how to get the amplifier parameters, and we will do this for the common source amplifier, so both configurations, the common gate amplifier and the common drain or voltage follower. So with every amplifier you are going to start off with a DC analysis, and for the DC analysis all your low frequency capacitors needs to become open circuits. So it's all the series capacitors at input, the output and bypass capacitors. Then you need to determine the Q point. For that we are going to use in the amplifier model. There is a video on DC analysis of amplifiers from start to finish. So the assumption is going to be that you already know how to find the Q point in this video, but we still do calculate the Q point, just not in such detail as a video on DC analysis. Okay, after the DC analysis you will do AC analysis. And the first step there is to identify the amplifier type. If you know the amplifier type, it makes it easier to know if what you're calculating and the values you are seeing are correct. Then all your low frequency capacitors will become short circuits. All your high frequency capacitors will be open circuits. Use the Q point that you calculated in the DC analysis to calculate your small signal parameters. You're going to switch off all DC voltage sources and all DC current sources. So voltage becomes grounds, currents becomes infinite impedances, so open circuits. Then we will replace the transistor with the model of the MOSFET. There's a whole video on the models as well. Then we need to calculate the amplifier input, output, and then the three gains: the maximum gain, the loaded gain, and the total gain of the amplifier. So first off, amplifier identification. So the best way is usually to check which terminal is common. So have a look where the input is, have a look where the output is. This is the gate, that's the drain. The one that is not connected to the input or output, that is the common terminal, and that will make this a common source amplifier. Okay, so similar goes for the PMOS. The common drain amplifier, or similar to the common collector or the voltage follower. Input on the gate, output on the source, and the common is here at the drain. So this is the common drain amplifier. Right, so that is how you identify your amplifier type. Next is, we always want to find these three parameters for amplifier. We want to find the maximum gain, the input impedance and output impedance, and from there we can figure out what will happen if we load this amplifier with different source and load impedances. Okay, so the maximum gain of amplifier is when this source is 0 and this load is infinite. That will give us the maximum gain of the amplifier. The loaded gain is when the source is short and we actually have a load. That is the loaded gain. So the AV that you will always encounter. And then the total gain includes this source resistor right here. Right, so this first one we find purely from the small signal parameters of the amplifier, and then afterwards we add the loading effects. Right, so the best way to learn this is to go with some examples. So we're going to have 3 examples on the common source amplifier, and then we will look at the simulations, then a couple on the common gate, and then a couple on the common drain amplifiers. Okay, so first up we have this common source with a voltage divider bias, no source resistor, and the transistor we're using here has a transconductance of 100 milliamperes per volt squared and a threshold voltage of 1.5 volts, channel length modulation of 0.01. Okay, so first DC analysis, find the Q point, then all the parameters. We will follow this recipe for all of our amplifiers. Right, so first let's draw the small signal model that will look like this. So going back, all of our low frequency capacitors becomes open circuits, so that falls away and this falls away for our DC analysis, so we are only left with this part here in the middle. Right, so in this all of the capacitors is gone. The one should be sitting here with the load. This is the small signal model, so not for the DC, this is for the DC. So with that, we can calculate the gate source voltage, and for the MOSFET, that is a pure voltage divider between these two. So the VGS value is 1.634 volts. We can plug that into the current equation, and that will give us our drain current. Okay, so that's 100 milliamperes per volt. That is 1.5 volts. And that gives us our drain current. With this configuration, we only have one resistor. So our Q point would be our VDD minus IDRD, which gives us 9.97 volts. Right, so now that we have our ID value, we can calculate our small signal parameters from that. So there is a couple of equations for transconductance. The more useful one when you have a Q point is the root of the drain current multiplied by the MOSFET's transconductance multiplied by 2, and that gives us a transconductance of 13.4 milliamperes per volt. We can also calculate the output impedance of our transistor if we have the channel length modulation, that's 0.01 per volt. So 1 over lambda IDQ gives us 111 kilo ohms. Okay, when lambda is unknown, we just assume that R out is infinite and it will also fall out of a model. It won't be there. Right, so with all that done, we can calculate all the parameters of our amplifier itself. So first up is the input impedance, and that is when we're looking into the amplifier from here, so without this signal resistor. And since this is an open circuit, we have only these two resistors in parallel, and that gives us 196 kilo ohms. Right, easy enough. Output impedance is when we are looking into the amplifier from there, ignoring the load, so it's RD parallel with R out, and that gives us 5.33 kilo ohms. Next, we have our gain. So this is still the voltage input of our amplifier, so small VGS multiplied by the transconductance of this current source, and our current source here, or the transconductance of it, can be multiplied by these resistors to give us our gain. So these two together is just our output impedance. So our gain is minus the transconductance multiplied by the output impedance, because this current source flows inwards, so it's a negative, and that will give us minus 71.42 volts per volt, or 37.07 decibels of gain. Right, and there is a gain of our amplifier. And with that, we have input impedance, output impedance, and our maximum gain. So from there, we can calculate our loaded gain AV. So with that, we just use the voltage divider across the load with the output impedance, and that gives us minus 57.5 volts per volt. And for the total gain, we just add the input impedance and this signal resistor also as a voltage divider going into the amplifier, and that gives us minus 44.72 volts per volt, or about 33 decibels. And that is the complete analysis of our first common source amplifier. So these MOSFET amplifiers is quite easy to analyze if they have no source resistor. The second one is a little bit more difficult with the included source resistor. I'll show you in a moment why, but it's nothing to worry about. So let's look at the problem. So we have dual rail. So RS here is responsible for our bias. RG is our input impedance, and RD is responsible for our gain. Okay, so we have VDD, VSS is plus minus 10 volts, a transconductance of 10 milliamperes per volt, 1 volt threshold voltage, and 0.02 channel length modulation. Right, so for DC analysis, that half of a circuit falls away, that half of a circuit falls away, and this here resistor will be visible. And for the small signal model, if this becomes a short, it will be visible. If this becomes a short, this resistor will disappear, and that becomes a short, the load will be visible. Right, so small signal model, see no RS would be visible, RG is our input impedance, and RD is our output impedance, given that R out is fairly large. So, DC analysis wise, this is a bit more tricky than that you're used to. And let's wipe away all of these slides. Okay. Our VGS is sitting right here. Okay, so we can take our loop voltage right there. So we have IGRG, which is 0 because the drain current is, the gate current is 0. And then we are left to VGS and VSS and IDRS. Okay, so we have RS, IDQ, VSS, and VGS. And from there we have our drain current that we can plug into this equation right here, and we end up with this monstrosity of our source resistor times the current plus VSS plus VGS, and it becomes easier if we just plug in all of these values, and we have 410 VGS minus 1 squared minus 10 plus VGS. Okay, so if we multiply this in VGS minus 1 squared, we get a quadratic equation. Okay, and that is kind of the difficult part of all of this, when you can solve the quadratic equation with that quadratic equation solver, which is minus b plus minus b squared minus 4 times a c over 2 times a, where that's a, that's b, and that is c. Okay, so this will give you two results. We get 1.157 and 0.845. Now we need to choose which one is our actual VGS value. So the assumption, since we're working with amplifier, is that we are working in the saturation region. Now for saturation region, our VGS value must be smaller than our drain source voltage, right? And this second value right here is smaller than our threshold voltage. So this one is in the saturation region. This one right here, our transistor will be off. So it's more likely that our VGS is the 1.157 volts. Okay. With that, we can calculate our drain current. So minus VSS minus VGS over RS, and that's 108 microamps. And from there, we can just calculate our VDS value. Okay, with our drain current, we can calculate our transconductance easily, 1.47 milliamperes per volt, and our output impedance is 463 kilo ohms. So there's our Q point, there is our small signal parameters, and now we can calculate our amplifier parameters. So our input impedance is when we are looking in from here. So RG is our input impedance. Output impedance is RD parallel to R out. That's 42.7 kilo ohms. And our gain is minus 62.7 volts per volts, or 36-ish decibels, multiplied by the loading factor on the output, minus 32.85 volts per volts, and loading factor on the input, since these two are exactly the same, half of 32.85 is 16.43, and that's 24.31 decibels. Okay, so all of this is kind of easy for the analysis. The difficult part here is to find our gate source voltage, to find our drain current. Okay, so with the additional source resistor, we have to solve a quadratic equation and then figure out which one of the two is our actual gate source voltage, working under some assumptions. Okay, example number 3 is our split source configuration. So this resistor is for our bias stabilization, and this one will have a huge influence on our gain. Right, so what do we have? We have a transconductance of 10 milliamperes per volt, 0.02 channel length modulation, and a threshold voltage of 1 volts. Right, so with DC is easy. That disappears, this disappears, and this resistor is not seen in our DC analysis. So we will have a very similar problem than example 2 to calculate for our DC analysis. But in our small signal model, when that capacitor becomes a short circuit, these two resistors will be in parallel with one another. However, since RS2 is much smaller than RS1, RS2 will typically be the dominant value right there. Okay, so this model is set up with the assumption that, oh, we can actually see it, but with RS2 being dominant, that is the only resistor we need to include in this model. So let's hop into our analysis. Now, since we are using exactly the same resistors that we had in this problem right here, so 82 kilo ohms for our source, and we have exactly the same transistor, the DC analysis ends up to be exactly the same, and our drain value at the Q point is 108 microamperes. Okay, so we're not going to go through this whole exercise again. We have a similar drain source voltage. Our transconductance is the same. Our output impedance is the same. The only addition here is RS2, and we have a bit of a different input impedance right there because our gate resistor was chosen to be very large. Okay, so our input impedance is now 1 mega ohm. Our output impedance remains the same since our RD is unchanged. But with our added source resistor, we have some degeneration going on. Okay, so we are just dividing by 1 plus the transconductance RS2, and that gives us a gain of minus 34.4 volts per volts. Right. So then we can again multiply by the loading factors, and we get minus 24.11 volts per volts with the load attached. With our input attached, since our gate resistor is 1 mega ohm, there is not much change from the loaded gain to the total gain because we are only loading it with 10 kilo ohms versus 1 mega ohm. Right, so remember that with a common source amplifier or any MOSFET amplifier, you get to pretty much choose your input impedance with a gate resistor right here. Okay, so let's have a look at our free simulations. That will give us an idea of how accurate these analysis was. So here is our first problem. Calculate measured the drain current at 894 microamps, VDS of 10 volts, AV0 of 75, 59.6, 46 volts per volts for the total. So before I run this, let's have a look here. It's 898 microamperes, almost 10 volts, almost 75, 57, and 44. 46 right here is fairly close to that 44 that we calculated. So, okay, this is the parameters that I extracted earlier on the simulation. So let's run the transient. We insert 20 millivolts peak. There's a first drop, and here is what we get over our load. Okay, so there is a fairly nice amplification going on. Here at 0.9 milliamperes, and here almost at 10 volts over our VDS right here. So I would say that our analysis by hand matches our amplifier in a simulation quite well. Let's quickly do AC, and here is our output, and that is 33.33 decibels, very close to what we calculated. Okay, so that is our first amplifier. Let me open the second one. So for the second simulation, I found a drain current of 104 microamperes, VDS voltage of 4.926. Then we have almost 70 volts per volt, 34 volts per volt, and 17 volts per volt. Let's see how that lines up with our calculated values. So 108 microamperes, 4.92 volts, 62, 32, and 16. That is fairly close to our simulated results. So let's run our simulation here. There's our current close to the 108 mark. Input of 20 millivolts. Since we have a matched input, this is roughly half. So that's 20 millivolts, that's 10 millivolts going in. And here is our output impedance, our output waveform, also half because of this resistor here being matched with the output impedance. Okay, so this is that minus 17.26 volts per volt. To give you an idea, if we make this 1 and make this 47 megs, that is the equivalent of a amplifier that's not loaded, so this AV0. And where is our output? Nice and large. Let's have a look at our AC simulation, and then we can see this in decibels. So 36.77 dBs, 36.78. Right. So our simulation and our analysis by hand lines up nicely. Okay, let me open the third and final common source simulation. Right, since this problem is similar to the first one in ID and VDS, we're not going to look at that, but AV0, AV, and GV, minus 38, minus 26, minus 26 roughly. Right here, let's see how that lines up with our presentation. So 30.7, 27, 27 decibels. So we look at these, they are fairly close to what we have in our calculations. These are a little bit higher, but the output impedance of this transistor will be much higher with this source resistor right here. Not totally in the scope of the work that we are doing right now. So the output impedance of this transistor increases when our source resistor is not um, bypassed like this. So if it exists in our small signal model, so our gain will be slightly higher, and that accounts for these increases. So let's just have a look at our impedance here. So 28 dBs, 28 dBs. Let's see our transient. So there's our input. Since our amplifier has a 1 meg input impedance, these two are lying very much on top of one another. So the input loading, don't want really large loadings, just put a very large resistor there on the gate. And there is our output impedance, our output signal, 20 milli in, 500 out. That is about 25. And boom, 25. Okay, so with a source resistor extra here, you can actually end up selecting your amplifier gain. Right, and that's it for our common source amplifiers. Let's go on to the common gates. Before that, let's look at the summary first. So in summary for our common source, for both cases, the resistance that we see on the gate is our input impedance. Output impedance is basically our drain resistor. Our gain is our transconductance multiplied by our output impedance. For designing, or when we assume that our output impedance of our transistor is infinite, GMRD would be our gain. And for this side, we need to degenerate the output with 1 plus GMRSS. And in a design, again, you have your maximum gain, similar to what we have on this side, divided by 1 plus GMRSS, right here. And those are the equations that you need to know for a common source amplifier analysis. Let's have a look at the common gate next. Okay, so input is here on the source, the output is on the drain. So, common gate. Right, so for small signal applications, these two resistors will be bypassed with this capacitors. So the only function of these two resistors is to bias our MOSFET. They will not be seen in our small signal when this becomes a short circuit. Okay, but for DC analysis, only this part here in the middle will be seen, and for AC analysis, this back part will go away. Okay, now typically for the common gate and the common drain applications, we are going to use the T model and not the hybrid pi model anymore. So let's have a look at what this amplifier will look like in a small signal. So right here, our gate is kind of grounded. So I'm drawing this as a 0 point because we will be seeing 1 over GM when looking into our amplifier. And if this is a ground, it is in parallel with our RS value down here. The output impedance will be these two resistors when looking in at the output. So very similar to that of our common source amplifier. Okay, So for DC analysis, we are going to go through the rigmarole again of calculating our gate source value. So first, we need to do this voltage division right here to find the gate voltage, and that is 5.42 volts. Okay, now the gate voltage is equal to our VGS plus IDRS in this application. So plugging this equation in here will yield the monstrosity again, which is equal to our gate voltage. And going through all the simplifications, we end up with a quadratic equation again, and we will get two values out again. So with the assumption that we're in saturation, it will be 1.773 volts, because our threshold voltage is 1.5 volts. 1.2 is not viable if we are assuming our amplifier is switched on, because that will be in cut off. Okay, it's below the threshold voltage. So this is our VGS value, is 1.773. With that, we can calculate our drain current and our drain source voltage. So 3.65 milliamperes and 4.7 volts. So using this small signal, using this drain current, we can calculate our small signal parameters, 27 milliamperes and 13.7 kilo ohms for our output impedance. Note that we have 0.02 channel length modulation, but our drain current is quite high, so our output impedance of our amplifier will be quite low. Okay, so 13.7 kilo ohms. So what we learn from this is if we choose our drain current to be too high, our output impedance of our transistor will be very, very low. Alright, with our transconductance, we can now calculate the input impedance of our amplifier, and as I said, we are seeing this 1 over GM in parallel with RS. So that will yield 35.7 ohms. Our output impedance is our RD parallel to our R out. So 932 ohms. The gain for the common gate amplifier is the same as the common source, it's just not inverted. So we get 25.16 volts per volts. Adding the loading effects, 23 volts per volts and 9.6 volts per volts with the input. Right. If we look at the input here and the source size that we're adding, the source size is about 50. This amplifier is actually a little bit mismatched. Typically, you want to design these with a matching input impedance and signal. These amplifiers are more typically used for high frequency applications, and there you generally work with matched input impedances and transmission lines or antennas. You want everything to be the same. Right, so just as a side note, so this is our first common gate amplifier. Our second amplifier is the dual rail. So we only have a one gate resistor here. Can choose it whatever you want. It's only there to finish this loop here at the back. So RS and RD is the only ones going to have influence here. let's have a look at the analysis. So this is something that you need to practice, is to get to these quadratics and solving them. Our threshold voltage is 1.5. So with the assumption that we're in saturation and our transistor is on, 1.6 is our more viable option than the 1.4 volts that we're having here, because for this one the transistor will be off and that one we will be in saturation. So let's go with 1.6, and if we use 1.6 volts we get a drain current of 466 microamperes and a VDS value of roughly 7 volts. Okay, going forward with our drain current, 9.65 milliamperes per volt, 107 kilo ohms output impedance. Calculating our input impedance, 1 over GM parallel to our RS here, 103 ohms. So you'll find that this one is a bit better matched than our previous problem. Our output impedance, this is 107 kilo ohms. This is 10 kilo ohms, so it will be much closer. This output impedance is fairly large, so 9.1 kilo ohms. The gain of our amplifier will be 88 volts per volts. We add the load, 67.7, and with the input loading, this should be half, so about 34.7 volts per volts. Right, then that is the analysis of this common gate amplifier. So these goes quite quickly if you get past this gate source calculation right here. So in summary, before we look at the simulations, the input impedance is RSS parallel to 1 over GM. If you use a current source here to bias this, input impedance will be just 1 over GM. So the much greater RSS can go, the much closer to 1 over GM this input impedance will become. Right, so there we have that. Output impedance, RD parallel to R out. The larger R out can be, the closer the output impedance will become to the drain resistor, and the gain is GM RD for this amplifier. Okay, so let me open the simulations and have a look at them. Right, so here is our first simulation. And drain current 3.65 milliamperes, VDS of 4.7 volts, 27, 24, and 10 volts per volts respectively. And let's see, 3.6 milliamperes, 4.7 volts, 25, 23, 9.6. So I think this is fairly close to our calculated values. So let's run our simulation and see. So inserting 50 millivolts, that gets dropped down very far because of the mismatch we have on the input. So that becomes roughly 20 millivolts going in. And there is our output. So about 500 divided by 20 is, yeah, that's close to 25. And that's our common gate. Let's do a AC simulation here. So there is our gain at 20.2 decibels, and this will increase if we make this input say 1 milliohms and no input loading. That went up by quite a lot, 23 decibels. And this, sorry, that's on the edge there, so 27.8. And let's make this load ridiculously large, and that will be the maximum gain of our amplifier at 28.63 dBs. And that is our common gate amplifier. Let me open the second simulation. Okay, so we have a drain current of 467 microamperes, 6.93 volts VDS, 96, 74, 37. Okay, 466 microamps, almost 7 volts for our VDS. 88, 37, 34. So these values correlate quite well with our analysis values. Let's run this amplifier. Let's see, 50 millivolts input, around about 25 going into the amplifier. So this is 100 milliohms looking into this amplifier roughly. And there is our final output. Okay, let's have a look here at the AC simulation. 31.5 dBs. Which is very close, well, to what we originally wanted or found in the analysis. So that is our common gate amplifier. Let's move on to the common drain amplifiers. So our common drain or voltage followers, you'll see that the input impedance is dependent here on RG1 and RG2. The source resistor right here is responsible for our current, and our input is basically a 1-to-1, so AV0 is equal to 1 with some loading effects then from the input and the output. Alright, so first let's work on this Q point, and again with this quadratic equation to solve. So here we will find something that is fairly large, VGS of 2.4 volt. Our threshold voltage is 0.5. So this amplifier will be on, and that is straightforward, just a negative value. So we don't even need to worry about the one if it becomes a negative like this. Okay, so we have a VGS of 2.4 volts, calculating the drain current 181.2 milliamps. I just realized, not realized, but I actually know this. You can calculate this drain current in two methods. When you get VGS, you can either use the one from Kirchhoff that we have, or you can plug everything back into this equation to find your drain current. This method is the easiest of the two. That's why I tend to forget about this one, but as a side note, you can use this equation also to calculate your drain current. Anyways, that will yield a VDS voltage of 6.5 volts, and with this we can calculate our small signal parameters. So transconductance of 190.4 milliamperes per volt. Due to our large drain current, we have a very low output impedance, 5.52 kilo ohms. And from the small signal, we can now calculate our input impedance and whatnot. So the first thing to remember when looking at this small signal model right here is that we have zero current flowing into this amplifier, and that is just as a reminder that we are looking at a open circuit here on the input of this amplifier. Okay, so RG1 parallel to RG2 is our input impedance, and that's 40.8 kilo ohms. Our output impedance is 1 over GM parallel to RS right here, and that is 4.72 ohms. Okay, so since this is a driver circuit, this must be a very small value. Okay, so a follower AV0 is 1 volt per volt or 0 decibels. The thing that's affecting this amplifier is typically the load right here. So the AV of this amplifier would be this RS parallel to R load, or it would stand more out if you call it R load prime. That's the typical thing it's named. I just use it like this right here to explain that we actually see these two in parallel with one another. So we have those two over 1 plus GM plus themselves again. So if you multiply with GM on top, we have GM RS parallel to R load over 1 plus GM RS parallel to R load. Okay, so R load here, 1 over GM here is basically our output impedance. So we will find that our loaded gain of this amplifier is 0.59 volts per volt or minus 1.32 decibels. Okay, minus because it's less than 1. If we include the effect of a source resistor, we have one big voltage divider here on the input. That will bring us down to minus 5.07 dBs. On to the next one. So here we have a common of a dual configuration. And for the dual configuration, we have 1.782 volts VGS. Calculate our drain current 82.2 milliamps. VDS value 11.78. Okay, so VDD plus a little bit extra into the range of VSS. That is for our swing. And we will find a transconductance of 128 milliamperes per volt, 12.16 kilo ohms output impedance. So our input impedance is purely the RG value that we have. Our output impedance, RS parallel to 1 over GM. These are still much smaller than this R out, so we don't need to worry about that too much. And we will find 1.26 dBs, and due to our bigger input impedance for this one, minus 2.94 dBs right there. Right. Our last common drain problem is the class A amplifier when we have a current source in here. So basically with that we say, okay, our drain current is 100 milliampere. So we don't need to go through the whole rigmarole of doing the quadratics, and we can plug this purely into this equation to find our VGS value, 1.914 volts. The current source will bias our transistor at the current that we want, and with that we find our Q point, 11.914 volts, pretty much the same as the previous problem. Transconductance 141.4 milliamperes per volt, output impedance of 10 kilo ohms. Okay, output impedance is now 1 over GM because the perfect current source has no RS, so it will be closer to 1 over GM, so 7.07 ohms. Our gain now becomes R load over 1 over GM plus R load minus 1.15 dBs, and with a large input impedance, I use the very large signal resistor, we now have minus 2.83 decibels right there. Building common drain amplifiers with current sources are typically the best way to do this. So before we go to the simulations, in summary, our input impedance is RGG. R load prime is RSS parallel to R load. So this is R load prime that you will typically find. Output impedance is RSS parallel to 1 over GM. So our gain unloaded is typically 1 volt per volt. Loaded, we have R load prime over the output impedance plus our R load prime. So if RSS moving towards infinite and R load being R load, our amplifier output here will simplify very much. See, I need to remove these primes here. In any case, the common drain is fairly straightforward like that. So let's open our simulations to see how it correlates with our analysis. So for our first common drain amplifier here, we have a drain current of 181.2 milliamps, VDS of 6.5 volts, 0 dBs unloaded, 1.33 decibels, minus 5.06 decibels, and let's see how that looks. 181 milliamperes, 6.5 VDS, 0, minus 1.32, minus 5.07 dBs. Okay, so the results that I extracted earlier from this simulation correlates very well with our analysis. So first up, we have our AC analysis right here. So this is with all loading effects, minus 5.06 decibels. And if we increase this load to 100k and remove a signal, we'll find that this is fairly close to 0 decibels. 920 milledecibels. So let's have a look at our amplifier in the time domain and see what we get. So the 8 volts input here, it drops down due to this voltage divider effect, and the final output is just fairly or a little bit smaller than our final output. So to demonstrate this, let's run it like that. Okay, we are driving it a bit into saturation. Let's make that a 4. See, our input and our output is very close to one another. It's only this small drop of 1.33 decibels, like that. Current, here in the center we have 180, and if we measure here, if we subtract this from 15, we get our 6.5 volts roughly. So our amplifier correlates quite well with what we analyzed. Let's have a look at the second one. So for the second one, 82.2 milliamps, 11.782 volts, and 1 volt, 0.8.7, 82.2, 11.78, 1 volt, 0.8.7. So our simulation correlates quite well with our analysis. Here's our input. There is our input after the voltage division, and there is our output with the load. Okay, so when it's through the amplifier. Right, so our common drain amplifier here is actually correlating very, very well with our calculated results. Let's have a look at our current source problem. So for our current source problem, we have our ID as 100 milliamps. So this current source right here just takes over, making our life easier with the calculations. VDS of 11.9, 1.9 roughly 0.7, 100 milliamperes, 11.9, 1 volt, 0.87, 0.722. That is very well with the calculations versus the model. So if we run this, we first have our AC, so minus 2.8 decibels. We are more interested here in the DC analysis. So if we run it like this, you can see that this is running right on top of that 100 milliamperes of a current source, and that is at minus 1.8. So 10 minus 1.8 is 11.8. So we zoom in, that will be closer to 0.9. Yes. There's our input. There is our input after the loading effect, and there is our output. So our simulations and our models is very well aligned with one another, and that is it for this long video. I do apologize, but tackling all three amplifiers analysis methods in 1 hour is not too bad. So that's how we analyze the common source, the common gate, and the common drain amplifiers. The next three videos will be on the designing of these three amplifiers. So thank you for watching.